So we're on to the 2025 MIT Integration B regular season set of questions. We'll look at the first 10 problems in this video, and in the next video we'll look at the next 10 questions. So the first problem happens to be the definite integral from x equals to 0 to x tending to infinity of 1 over the square of x plus 1 plus 2 times the square root of x. Problem number 2, an indefinite integral of x squared times the cosine of the arc cosecant of x. Problem number 3, the definite integral from x equals to 0 to x equals to 1 over 2025 of the summation from k equals to 1 to k tends to infinity of the kth term of 2025x times e to the power negative 2025x all over the k factorial. And yeah, so this is interesting. And then problem number 4, the indefinite integral of 1 over 1 minus x to the 4th power. And problem number 5, the definite integral from x equals to pi over 2 to x equals to pi over 2. From x equals to negative pi over 2 to x equals to pi over 2 of cosine of 20x times cosine of 25x. Problem number 6, the definite integral from x equals to negative 2 to x equals to positive 2 of the maximum value of either x or x squared or x cubed. So interesting problem. Problem number 7, we have the definite integral from x equals to 0 to 2025 of the sawtooth function of the square root of x. Problem number 8, the definite integral from x equals to 0 to x equals to pi 2 pi of the absolute value of sine x plus a half. And problem number 9, an indefinite integral of x times open bracket half plus the natural logarithm of x close bracket times the natural logarithm of the natural logarithm of x. Problem number 10, the indefinite integral of cosine to the 4th power of x minus 1 over sine to the 8th power of x. So that is the complete problem, the complete set of the first 10 problems of the MIT 2025 Integration B regular season set of questions. So let's go and see how we may be able to solve each of these problems. So this problem is interesting. Problem number 1. I look at the denominator and I see something that gives away. This seems to be a binomial expansion of square root of x plus 1. So what I do is I incorporate that and it simplifies to 1 over the square root of x plus 1 squared, which is to the power 4. Okay. And so we can say let u be equals to square root of x, as it is the norm for me. I try to substitute off the complicated variable or function, and so what that means is that u squared is equals to x, and then when I differentiate both the left and right hand side, on the left hand side we have 2u du dx, on the right hand side we have 1, and so we can substitute for dx with 2u du. Now the limits will remain the same as x tends to 0. When x equals to 0, u will be 0, and when x tends to infinity, u will still tend to infinity. Infinity is such an interesting concept. Anyway, so in the x domain, we do have what we have here, but now when we transform it to the u domain, in place of the square root of x in the denominator, we have u. In place of dx, we have 2u du. And we can pull 2 out so that now we do have an integral from x equals to 0 to extend, from u equals to 0 to u tending to infinity of u over u plus 1 to the power 4. I don't really like having a summation in the denominator, so what comes to mind is I could now substitute the complex component in the denominator, and I'll say let y be equal to u plus 1, which means that dy du is 1, and so we can substitute for du with dy. So previously the substitution with y for u plus 1 means that we have in the lower limit 1 when u is 0, y is 1, and obviously infinity remains infinity, but also u becomes y minus 1, and then the denominator u plus 1 is y. So that now allows us to now divide each component in the numerator with y to the power 4. So we have 2, the integral from y equals to 1 to y tending to infinity, or 1 over y to the 3, and then minus 1 over y to the 4th. So that is an easy integral to work with. And so we have negative 1 over 2 y squared plus 1 over 3 y cubed. And so applying the limits appropriately, 2 times the limit as y tends to infinity of this expression means that everything here tends to 0, minus limit as y tends to 1 of this expression means that we have negative 1 over 2, y is 1, so negative a half, plus 1 over 3. And so that means we just have twice half minus third, and that means we have twice times 1 over 6, and that is 1 over 3. So that is the answer that was being looked for. I think if you looked at the answers, this is what was being asked for. So if you have any question in this regard, please don't hesitate to reach us. And just leave a comment on the comment section if you have any question. So we're going to problem number 2 next. Problem number 2 is an interesting one, and I think what is being tested here is re-expressing the arc cosecant of x in an expression that has the arc cosine. And what I'll do here is just begin by saying let y be equal to the arc cosecant of x, such that the cosecant of y is equals to x, and that means that now cosecant of y is 1 over sine y, which is equals to x, and then I could multiply both sides by sine y and divide both sides by x, so that I have 1 over x equal to sine of y, and then now we can express the left-hand side as 1 minus 1 over x squared is equals to the square root of 1 minus sine squared, which is cosine y. And so the arc cosine of y, the y is equals to arc cosine of the square root of 1 minus x squared. And so we can plug back y into this expression. So the integral of indefinite integral of x squared times the cosine of arc cosecant of x is the same as the integral of x squared times the cosine of the arc cosine of the square root of 1 minus 1 over x squared. So the cosine and the arc cosine cancel one another, and so we are now left with x squared times the square root of 1 minus 1 over x squared, which simplifies when we take one of the x's into x squared minus 1. And so this is an easy integral because this is the same as the integral of the derivative of 1 over a third x squared minus 1 to the power 3 over 2. You can prove it out, or you can decide to use the trigonometrical substitution, but But yeah, this is straightforward. So that when you differentiate x squared minus 1 to the power 3 over 2, you get 2x times 3 over 2, and the 2 cancels, and you have 3, and so to cancel 3 in this expression, you have a third here. So the answer now becomes, since the integral is the antiderivative expression, so we have a third times x squared minus 1 to the power 3 over 2 plus integration constant c. As simple as that. And that was the answer that was being sought for. Now, moving forward to problem number 3, the definite integral from x equals to 0 to x equals to 1 over 2025 of the summation from k equals to 1 to k tending to infinity of 2025 x to the power k times e to the power negative 2025x over k factorial, means that we can pull out whatever is not really limited or restricted by the summation sign. So we can pull out the e to the power negative 2025x, and we are left with an expression which is a summation from k equals to 1 to k tending to infinity of 2025x to the power k over k factorial. The definition of e to the power x is a summation from k equals to 1 to k tending to infinity of x to the power k over k factorial. So our expression here now becomes the integral from x equals to 0 to x equals to 1 over 2025 of e to the power negative 25x times e to the power 2025x. And so using the rules of indices or exponents, these add up and we have a 0, so we have e to the power 0, which is 1, and that means that our integral is x, and the limits as shown here. So we have 1 over 2025 minus 0, and the answer is 1 over 2025, which was the answer that was being sought for. Going on to problem number 4, which is the indefinite integral of 1 over x to the power 1 minus x to the power 4. This is the same as the integral of 1 over 1 minus x squared. Using the difference of two squares, this means that now we do have 1 over 1 minus x squared times 1 plus x squared. We can now express this as a partial fraction, as half the integral of 1 over 1 minus x squared plus 1 over 1 plus x squared. Why? Because when you multiply the denominators and you add up 1 plus x squared plus 1 minus x squared, you have 2 in the numerator, and so to cancel that 2 out so that you have a 1 as shown here, we have a half here. And then 1 minus x squared can also be expressed as 1 minus x times 1 plus x. And then using the same trick we used above, so we have half times a half, 1 minus x plus 1 over 1 plus x. And then we have half the integral of 1 over 1 plus x squared. So we have now a quarter, the integral of 1 over 1 minus x plus 1 over 1 plus x plus half the integral of 1 plus x squared. This is easy to see that this is negative quarter, the natural logarithm of 1 minus x squared, plus a quarter, the integral of natural logarithm of 1 plus x squared. And this is obviously a famous integral, so we have 1 plus that, which we have plus 1 over 2 arctangent of x plus c. So we can re-express this using the rules of logarithm, where we have a quarter natural logarithm of 1 plus x over 1 minus x plus a half arctangent of x plus the integration constant. So that is the answer that was being sought for. If you have any question as to how this came about, feel free to leave a comment in the comment section. We'll get back to you as fast as possible. Then on to problem number 5, the definite integral from x equals to negative a half, pi over 2, to x equals to pi over 2 of cosine of 20x plus times cosine of 25x. Here we will just use these normal trigonometrical identities where cosine of a plus b is equals to cosine a cosine b minus sine a sine b. Cosine a minus b is the same as cosine a cosine b plus sine a sine b. And then when you add the left hand expressions here, we have cosine a plus b plus cosine a minus b is the same as twice cosine a cosine b, and so that means that when you divide both sides by 2, it means cosine a plus cosine a times cosine b here is the same as half of cosine a plus b plus cosine a minus b. So taking a to be 25x and b to be 20x, we can now say that our expression is the integral of half cosine 45x, which is a plus b, plus cosine 5x, which is a minus b. And so this is easily integrated. So we have a half 1 over 45 sine 45x plus 1 over 5 sine 45 sine of 5x. Applying in the limits, because this is continuous in this domain, we just substitute the limits. We have and subtract the upper limit and subtract the lower limit. We have 1 over 45 sine of 45 times pi over 2 minus sine of negative 45 pi over 2 plus a fifth sine of 5 pi over 2 minus sine of negative 5 pi over 2. So this negative here propagates out, and all of a sudden you have, since these are odd values, this becomes 1 and this becomes 1, and so you have half of 2 over 145 plus 2 over 5, and here we've just explicitly shown what happens. So 1 minus minus 1 is just 2. Now, if that's the case, we have 1 over 2 times 2 over 45 plus 2 over 5, and then the half cancels is 2, so we have 1 over 45 plus a fifth, common denominator 45. We have then 45 here becomes 1 plus 45 divided by 5, we have 9, so 1 plus 9, that becomes 10 over 45. Divide by 5 in the numerator, we get 2. Divide by 5 in the denominator, we have 9. So the answer is 2 over 9, and that's what was being sought for. Problem number 6, the integral from x equals to negative 2 to x equals to 2 of the maximum value from within a pool of x and x squared and x cubed. Now it's very important to see that in the domain from negative 2 to 0, all the values x and x cubed are negative, but only x squared is positive. So the maximum value out of this expression is going to be x squared plus from 0 to 1, because these are values less than 1, the square and the cube of those values will be less than the actual value. So x, it tends to be maximum in that span. As soon as you cross 1, the highest power gives you the maximum value. So x cubed tends to be the maximum value between 1 and 2. So you have these three integrals between negative 2 and 0, we have x squared. Between 0 and 1, we have x. Between 1 and 2, we have x cubed. And so when this is integrated, you have x cubed over 3, the limits as being negative 2 and 0. Here, between 0 and 1, we have x squared over 2. Between 1 and 2, we have x to the power 4 over 4. And so when you apply the limits, we have 0 minus 2, negative 2 cubed is going to be negative 8 over 3. And then we have 1 over 2, 1 squared over 2 minus 0 squared over 2, which is just 0. And then here we have 2 to the power 4, which is 16 over 4, minus 1 at the power 4 over 4, which is 1 over 4. And so we can now get the common denominator being 12. 12 divided by 3 is going to be 4. 4 times minus of 8, which is positive 8, which is 32, plus 12 divided by 2 is 6. 6 times 1 is 6. And then we have 12 divided by 4 here is going to be 3. 3 times 16 is 48. 12 divided by 4 is 3. 3 times 1 is 3, so we have minus 3. And 48 plus 32 is going to be 80, plus 6, 86 minus 3 is going to be 83. So the answer is 83 over 12. Problem number 7, the definite integral from x equals to 0 to x equals to 2025 of the sawtooth function of square root of x. So this is the same as the integral from x equals 0 to 2025 of the square root of x minus the floor function of x. So it's that residual value that you have of a specific function over its floor function. And the first part here is very easy to integrate. We can separate this into two separate integrals. So we have this integral of square root of x from x equals 0 to 2025, and then now we can also separate the integral of the floor function of the square root of x from 0 to 2025. So a quick thing here, so we can just integrate the square root of x to 2 over 3, x to the power 3 over 2, and then the floor function will leave it as it is for now. And so applying this limits appropriately, we get 2 over 3 times 2025 the power 3 over 2, and that becomes 2 over 3 times the square root of 2025 is 45 times 2025. So this is what we get here. And now we can multiply 45 by 2 over 3, we get 30, so it is 30 times 2025. Let's color our integral of the floor function as blue, because it is important. What that means, the floor function means that the floor function of the square root of x means it's equal to k when the square root of x is between is greater or equal to k and less than k plus 1. What that means, that happens when x is greater or equal to k squared but less than k plus 1 squared. So what does that mean? The integral of the floor function of the square root of x is that you have some constant values. So we're going to have k between when x is between x squared and it's between k squared and k plus 1 squared. So we are going to have discrete values, and that's why now we're introducing the summation sign here, because we have this we do have discrete values in the intervals k squared and k plus 1. And it's important to know that at the square root of 2025, which is 45, we have only one value. So the extent of the k stretches up to 45 minus 1, which is 44. So our summation becomes k x integrating k with the limits applied appropriately, and the sum now becomes k plus 1 squared minus k squared, and that means that using the difference of two squares, we have k plus 1 plus k times k plus 1 minus k, and that becomes k times, this is 2k plus 1, and k plus 1 minus k just becomes 1. And so what we're left with now is the summation of from k equals to 0 to 44 of 2k times k is 2k squared plus k. And we know that the integration of a k squared from k equals to 0 to n is n times n plus plus 1 times 2n plus 1 over 6. And the integration, the summation of k from k equals 0 to n is this 2 times n plus 1 over 2. So using these six formulas, we can just go ahead and say that we have twice the n is 44 times 44 plus 1 times 2 times 44 plus 1 over 6 plus n 44, n plus 1 is 44 plus 1 is 45 over 2. So this reduces to 44 times 15 times 89. Why? Because 2 times divide by 2 here, divide by 2 we have 3, 45 divided by 3 is 15. And here 2 44 divided by 2 is 22, so we have 22 times 45. So this you can check it out, but we get 59,730. And now plugging back our expression where our integral was now 2025 times 30 minus the blue integral. The blue integral we have deduced it to be 59,730, and this, when you work it out, it becomes 60,750. So 60,750 minus 59,730, we get 1,020. So that's the answer that was being sought for. If you have any question, please feel free to reach out. So this is an interesting problem. It just requires a lot of intuitive stuff, but let's just see how one would quickly deduce the answer. So the integral, indefinite integral from x equals 0 to 2 pi of the absolute value of sine x plus 1, sine x plus 1 over 2 means that when the expression under the absolute sign is negative, we apply a negative sign. So we have a quick plot. I use Desmos. So the initial plot of sine x is that function, the red function that oscillates, the plot that oscillates around 0. And then when you add half, that gets an offset. So we have the blue function, but as soon as you apply the absolute value where it crosses the negative side, that gets flipped out into a positive. So we just have to deduce when where these points are, and then between this, in this domain, in this region, we just apply a negative sign. So what that means is that we just have to find when sine x plus a half equals to 0, and that means that sine x is equal, at that point sine x is equals to negative a half, and that we know to be when x is equals to pi plus pi over 6 and 2 pi minus pi over 6. And so our integral just becomes the normal integral from x equals 0 to pi plus pi over 6, and then in the interval of pi plus pi over 6 to 2 pi minus pi over 6, we apply a negative sign, and in the last interval we just keep it the way it is. And when we integrate that, we get negative cosine of pi plus pi over 6 minus cosine of 0 plus a half of pi plus pi over 6 minus 0. And here, obviously, since we have a negative of sine x, it's become cosine with the limits applied. And again, going down, negative a half, so we have negative a half here, upper limit minus the lower limit, and then back here we get negative cosine 2 pi minus cosine 2 pi over 2 pi minus pi over 6 plus a half of x, obviously, upper limit 2 pi, lower limit 2 pi over 6. So when we quickly work this out, we're going to get, so we quickly work out what we had previously. We get here we get negative cosine pi plus pi over 6 is negative root 3 over 2 minus cosine of 0, which is going to be minus 1, plus a half pi plus pi over 6 minus 0. We're left with pi plus pi over 6. And then here we have cosine of 2 pi minus pi over 6. We get positive root 3 over 2 minus cosine 2 pi plus pi over 6 is negative root 3 over 2. So we have negative root 3 over 2 here, minus what we have here is just minus a half. The upper limit 2 pi minus pi over 6 minus pi plus pi over 6 results in 2 pi over 3. And down here we get cosine of 2 pi is 1, cosine of 2 pi minus pi over 6 is root 3 over 2, so we have 1 minus root 3 over 2. And here we have 2 pi minus 2 pi over 6, we have just pi over 6 left. So plus a half times pi over 6. It's important to see that this becomes root 3 here. And here we have minus minus, we have root 3 over 2 positive, and then minus minus here plus 1. And then pi plus pi over 6 is 7 pi over 6. Obviously half is left there. And we have root 3 here minus half 2 pi over 3. We'll just leave it as it is here. And then minus 1 minus root 3 over 2. We'll keep it that way. So we see positive here, root 3 over 2. This also becomes positive root 3 over 2. So add up, we have twice root 3. And then we have 1 minus a half, which is going to be a half. And that would cancel out with this. So this negative a half and this negative a half would cancel out. And then we have the pi's adding up to pi over 3. And this is the answer that was being sought for. On to problem number 9. The definite integral of x times half plus natural logarithm of x times the natural logarithm of natural logarithm of x. The first thing I'll do is just multiply things out so that I just have a feel of where things are. And I can quickly deduce that there is a pattern. And that is that we do have a half x squared times the derivative of log of x that is hidden here, and the x here is the derivative of half of x squared. So with that in place, I can move forward and say, okay, I do have some things that I can pull out of the brackets, the log of x. But inside the bracket, I have half x squared times the derivative of log of x, and then you have the derivative of half of x squared times the natural logarithm of x. And using the product rule as regards differentiation, I could collapse whatever is in the bracket to the derivative of the product of half of x squared and the natural logarithm of x. And from here now I can use integration by parts, and integration by parts means that if you have a product of a function v and the derivative of function u, and you integrate that, you get uv minus the integral of the function u times the function, the derivative of v. And so our uv is just going to be equal to half x squared log x, natural logarithm of log of x, minus half x squared, so this is u, times the derivative of v, which is log of x. Going forward, that means that now we have half x squared log x times the natural logarithm of log of x, minus half x squared times log x. Differentiating log of x, we have 1 over log x times the derivative of log x. You can see this and this would cancel, and the derivative of log x is 1 over x. So one of the x's on the x squared would cancel as well. So as we said, this and this would go, this and the square would go, so we have whatever we had minus the integral of half of x, so which is just half x squared natural logarithm of x minus a quarter of x squared plus the integration constant. And that is the answer that was being looked for. The problem number 10, the indefinite integral of the cosine to the power 4 of x minus 1 over sine the power 8 of x. So the first thing I would do is I would express the cosine to the power 4 as cosine squared x squared minus 1 over sine to the power 8x, and so using a difference of two squares, that is same as cosine squared x minus 1 times cosine squared x plus 1, and then I would pull a negative 1 out so that I have 1 minus cosine squared x times cosine squared x plus 1 over sine to the power 8x, the power 8 of x, and 1 minus cosine squared x is sine squared x, so that I can replace 1 minus cosine squared x with, and so sine squared x and sine the power 8 of x would interact with one another, so eventually we have minus the cosine squared of x plus 1 over sine to the power of 6 of x. And then now I can divide each part, or first of all I could express 1 as cosine squared x plus sine squared x, so we have 2 cosine squared x plus sine squared x, and that means that now I have negative the integral of twice cotangent of 2 cotangent squared x times cosecant to the power 4x plus cosecant to the power 4x. Interesting thing to note, we could express cosecant to the power 4 as cosecant squared x times cosecant squared of x on both ends, and since we can express cosecant squared of x as 1 plus cotangent squared, so that we can quickly replace that with so that we now have the negative integral of twice cotangent to the power 4 x times cosecant squared x plus cotangent 2 twice cotangent squared x times cosecant squared x plus we have cotangent squared x times cosecant squared x plus cosecant squared of x. So these 2 and 1 here interact, so we have 3. So here we have 2 cotangent 4 to the power 4 of x times cosecant squared x plus 3 cotangent squared x times cosecant squared of x plus cosecant squared of x. So we can take a breather here. Cosecant squared of x is the derivative of cotangent of x, right? And then right here we can see that when we differentiate cotangent to the power 5 of x, we get 5 cotangent to the power 4x times cosecant squared x. So this now brings us down to 2 over 5 cotangent 5 to the power 5 of x plus 3 over 3 cotangent to the power 3 of x plus cotangent of x plus integration constant. Now you may as well just pull cotangent to the power 5 of x over 5 out, and that will lead you to an expression that is cosecant heavy, but I think we'll choose to stop here. because this is an equally correct answer. So thank you so much for hanging out with us through the 10 fast problems of the regular season MIT Integration B 2025. We hope you continue tuning in, because we're going to come with the subsequent problems, quarterfinals, semifinals, and also finals. This is Everyday Mathematics. What we do here is we love mathematics and we enjoy numbers. So until next time, adios.